Hello, this is Kan-Lin speaking. In this section, we're going to talk about the stack, the fuel cell stack. In previous, we've been talking about a single cell. The single cell, the output voltage is about 0.7 for a PEM fuel cell, 0.7 to 0.8 depends on your operating conditions. But that voltage is far lower than for any practical application. So you need to connect. We need to connect several cells in series to stack up the cell voltage. As we know, if we connect a single cell, connect in series, then the voltage is equivalent to the sum of individual cell voltage. However, the current, because they connect in series, so the current actually should be the same for each single cell. Usually, so far, the commercial stack is about the 60 cell connect in series. And that will give you the output voltage somewhere around 50 volt, somewhere around that range. But in practical, usually we had 100 in Taiwan. We had 110 volt AC. The reason we don't stack all the way to say 150 stacked together, because you had to know as other battery had the same situation. If any cell in the series had broken or degraded, then whole stack is suffer. So try to reduce the risk of the cell stack, single cell being degraded and will affect the whole stack. So probably so far we use about the 60 or 70 stack, single cell stack together as a stack. If you need 110 volt output, you might connect two cell stack in series. Then you may get about 100 volt. In that case, you go through the inverter, try to convert the DC current into the AC power output, and then from the converter stack up the voltage from maybe 100 volt AC to 110 AC. So that's the basic of try to connect together in series. How the physical we connect it will be shown on the next slide. This is the laminated stack layout. Over here we always talk about for a single cell, and the hydrogen coming in on the anode side, and the oxidize into the proton and diffuse to the cathode, and then electron will be going from external circuit and then coming to the cathode, and on the cathode oxygen diffused into the catalyst layer and reacted with the proton and then reduced by the electron and generate water. But if you connect in series, what happens? This is the stack together. Over here, inside here is a single cell. The single cell over here, the anode is right here, and then the cathode is over here, and this separate between the anode and cathode is a membrane here, and this is a flow channel I draw over here, the flow channel. So the flow channel, they carry out the over here the hydrogen going to the anode and then oxygen going to the cathode. So other cell will be connected together over here like this. So each one is single cell connected. Over here we may say there's a total of 1, 2, 3, 4, 5 cell connect in series. And then the current will be generated out from the current collector from here and then going out through the load. Over here we can see how the material and electron flow on the bipolar plate. This is the typical 5 cell we mentioned before, and then we're going to see how the electron or material flow through these two cells. These two single cell connect in series, and then the enlarged diagram is shown on the bottom. Over here, this is the flow channel for this cell over here, and this is the anode here, and then this is the membrane, and this is the cathode. So this is the first single cell here, and this is the second single cell here. The hydrogen will be carried out through the manifold to individual single cell. We imagine there's a manifold that will carry out the hydrogen and then through the flow channel and distribute to the anode side here and for the anode side here. The hydrogen through the flow channel, through the flow channel on the catalyst layer. And then on the anode side will be oxidized into the proton, and the proton will be migrated from the anode side to the cathode side. On the cathode side, there's oxygen. The oxygen will be also carried by the manifold to individual single cell. But the manifold carry out the oxygen do not mix with the hydrogen. They are carried by a different manifold. The manifold, the oxygen will be through the cathode side flow channel and react with a proton, diffuse or migrate from the anode side. On the anode side, the electron will be generated because hydrogen oxidation, but instead of go through the external circle, the electron generated on the anode side will be just conducted to the next cell over here, and this one will be shown easier from next one. You can see over here the hydrogen, the electron generated by the hydrogen oxidation on this single cell will be direct flow to the next cell and supply for the oxygen reduction reaction need. So over here, the oxygen reduction need, the electron will be supplied by next cell from here. So the electron current will be flow from one cell to the other if you think this way. And then the current opposite to the electron current flow will be flow from here to this direction. So the overall, this goes through the external current will be only for the stack only had a 2 current collector on both sides instead of single cell for each one. Only for the stack, only the current collector is only on the both end of the stack. Will be carry out the electron and circulate and complete the whole entire electron circulation. So this is the bipolar plate. We call the bipolar plate because one side of the flow channel is supply the hydrogen and electronically connect to the anode of this single cell. But on the other side of the plate is supply the oxygen and then connect electronically to the cathode side for this single cell. So for this plate, one side is an anode for this single cell, and one side is a cathode for this single cell. So we call it a bipolar plate. The flow channel on the cell on the flow channel, there's a different type: the parallel, serpentine, interdigit, and island type. The parallel flow channel is had a very low flow resistance. The coming in and like a multiple parallel channels, so the reactant going through here is very easy flow. The mass flow is much faster, and then going out, they had a high volume of the gas flow rate and the low resistance. But the problem for this, if you had a droplet on one channel, then the rest of they build out the pressure distribution. The rest will be going around. So this side of the if this one blocked by the droplet, the water droplet in a pan-filled cell, then there's no flow because the resistance here, the flow will be simply stopped, and eventually the catalyst around this channel will be no use, and it eventually will migrate to other channel. So there's a problem if there's a gas droplet accumulate. Eventually this channel will be die out. For the direct methanol fuel cell, they might have accumulated on the carbon dioxide on the anode side. In that case, the methanol, liquid methanol, just go around for other channel, and eventually this catalyst around this channel will be die out, and then will be propagated to other channel, just like a cancer. To overcome this, usually people use serpentine. Serpentine is only one flow channel. So you had a droplet around here or the carbon dioxide gas bubble in the channel. Eventually it will be pushed out because there's only one way to go. But the problem for this serpentine is mass flow rate is much lower because there's only one channel had to go through, and then pressure drop is very high. There's other like interdigit. This is a blind hole over here. So over here the flow had to go here, the terminate. They had to go around the GDL and then go to the other channel flow. This one will be make sure the gas will be forced flow through the gas diffusion layer and go to the other channel. This will be give a better mass flow rate for the in the GDL, but the problem is the pressure will build up. People also thinking about the island type but we find that in practical application, if you had a gas bubble formed over here, then because surface tension is hard to blow away. Or you had a droplet over here accumulate, then the droplet will hard to blow away. So this one usually been tested and eventually give up. Most popular flow channel will be somewhere between these two, parallel and the serpentine combination. We can see this is a typical flow channel. You can see over here there's a manifold here. The manifold here will be connected to the flow channel going over here and then going out from here. And the manifold here will not mix. There's no hole coming out this channel, but going to the opposite channel here. So you can see, and over here there's an O-ring. There's an O-ring to around the peripheral. So make sure there will be still gas tight over here. So the gas will not just flow outside and through here. It's have to go through the flow channel over here. On the bottom, this is called a manifold, and this is called a flow channel here. And over here is more clearly the gas inside here will be, there's a tiny hole channel, and then going through here, they drew the hole over here. So coming out those channel, and this channel will be flow through and evenly distribute the flow. So for individual channel is like a serpentine, but try to increase mass flow and reduce the pressure drop. So actually there's 1, 2, 3, 4, 5, 6 parallel channel flow through here. So you can see they had some kind of combination between the parallel channel and the serpentine channel combination use of it like this. There's another kind of stack layout we call the planar layout. The planar layout, this is the anode here for the one cell. There's an anode for second cell. This is the anode for the third cell. And this is the cathode over here. And this membrane separate between. Over here you can use a single membrane. And then over here the electronic connector is a metal mesh. So the reactant can come in or the gas can come in, but also the current can connect between one cell to the other cell. This kind of stack planar layout usually is for the cell phone or notebook because they are flat. So in order to connect make a cell is flat. Flat stack, we had to connect into the planar layout. In this case, for direct methanol fuel cell, you might have the methanol diffuse by the capillary action. You had a porous medium, so the methanol, liquid methanol, can be sucked into the stack by capillary action. This is called a passive feed because there's no active component. Or you can have the circulation pump through the methanol, pump through here. Then we call the active feed. And over here, the methanol will be coming out, and then over here will be the air over here, and maybe from the natural convection, or you had a blower blow through the air here. If you have blower blow the air through here, that's mean active feed. If you just natural convection, there's nothing going, just the air that in natural convection diffused into the air castle, then we call it the passive feed. The good thing for the planar layout is a flat stack, but the problem, the big drawback for the stack, for the planar stack, is the internal resistance very high, because you had to think the current had to conduct from the anode here. The electron had to flow from the anode to the cathode. It goes through a very long path. But with a very narrow cross section. If you remember the resistance, the resistance in the conductor is proportional to the diffusion or the conducting length. So the conducting length is very high, then the resistance will be increased, and then the cross section very low, the resistance also increase. That's a problem for the planar layout. It's only good for the small output power because the current is low, so the internal resistance due to this planar layout maybe can be neglected. But the high current, for instance, even to 20 watt above, then usually the planar layout may not be good because the internal resistance is getting too high, and the cell voltage just can eat it up by the internal resistance. So this is the typical for the stack layout over here, and then the air will be going inlet through those manifold, and then maybe going out from the other manifold, and the air may be coming out from here individual, and then going out from the other one. They stack together, and only the current both ends had a current collector, and the end plate had both, and they have screw right through the entire stack. So this is a typical photo for the stack that we call the short stack. Is only for demonstration purpose because 10 cells in connected together only give you about 7 volts, which is not really had too much practical application. Usually we stack about 60 stack together may generate say 50 volt in that case. And this is the hydrogen coming out and hydrogen going out. This through the manifold we show up before, and then the air in and air out. And this one for the low power output, any power below 1 kilowatt, usually for they had air cooling channel here. This air cooling channel. We can put one fan over here. We suck the air from the other end. For instance, we put a fan over this side, and will be suck evenly the air through those air cooling out. Because for a stack, the energy conversion efficiency for a pure hydrogen is about 50%. So you may imagine for 1 kilowatt output, you had to heat dissipate about another 1 kilowatt heat going out. So it's a huge heat that you had to carry out from the fuel cell stack. Otherwise, the fuel cell might burn out, may be too hot. not different from the single cell. The single cell only one MEA in the middle, and then a lot of heat can be dissipated from the outside the single cell surface area. But for the stack, you can see the heat dissipate for a single MEA is only on the outside here, very narrow. So you had to somehow can remove heat. You had to cooling off the stack. For a small stack, any power below 1 kilowatt, you can use air cool. But cooling the stack above 1 kilowatt, for instance 5 kilowatt or 10 kilowatt stack, then you had the air. You need air to circulate through the stack to cool out, because air cooling is much more effective than the air cooling. So far we've been talk about from the catalyst to MEA to a single cell to a stack. The next section we'll talk about the power unit, because even for a stack, they still need other balance of plant peripheral to make sure really entire system work. You have to control the flow rate, air, hydrogen, the temperature, humidification, and then make the stack only produce DC current. You have to convert into AC current and then to the high voltage. So that's a peripheral for the. We still need other things to make a fuel cell power system, and we'll be talking about that for the next section.